Hi. Now in previous videos we discussed about the ion exchange chromatography. Now in this video we are going to discuss how to select a particular ion exchanger and how to select a particular buffer for an experiment involving the ion exchange chromatography. So let's start with the selection of the ion exchanger. Now, while choosing a proper ion exchanger, one should consider the nature of the solute that he or she is going to separate. Okay, the nature of the solute is important while choosing an ion exchanger. Now, the choice of an ion exchanger, whether it is going to be a cationic exchanger or an anionic exchanger, that choice depends upon the isoelectric point of the biomolecule which is going to be separated. Okay, the biomolecule which you are going to separate, what is its isoelectric point? On that you will choose whether you have to use a cationic exchanger or an anionic exchanger. So if the solute molecules have only one type of the charged groups, then in that case the choice is simple. Okay, so if the solute is positively charged, then it will bind the cationic exchanger. So to separate that positive solute molecule, you will use cationic exchanger. And if the solute molecule is negative, then you will use anionic exchanger. Okay, so in case where the solute molecule has only one type of the charged group, the choice of the ion exchanger becomes quite simple. Now, the thing is that many solutes have more than one type of ionizing group in them. Okay, they may have both positively charged group as well as negatively charged group. And in this case, the net charge on this solute depends upon the pH. Okay, so the net charge can be positive or negative. It is either positive or it is either negative. So that net charge will depend upon the pH. But that solute will be having both positively charged groups and negatively charged groups. Now at isoelectric point, the solute don't have any net charge, and that is the reason why the solute will not bind to any type of the ion exchanger. Now if the pH value is above the isoelectric point while considering a solute, then that solute will be having a net negative charge and it will be absorbed by the anion exchanger. Okay, it is absorbed. So let me change that. Okay, so if the pH value is above the isoelectric point with respect to the solute, then that solute will be having a net negative charge and that solute will be adsorbed on an anion exchanger. But if the pH is below the isoelectric point, which is represented by Pi, then the solute will be having a net positive charge and it will be absorbed by a cation exchanger. So it all depends upon the pH. Okay, so consider this. Okay, this arrow is representing the pH of buffer. Okay, this is high pH, this is low pH. Okay, so when the pH is high than the isoelectric point, then this your protein will be having a net negative charge and it will bind to an anion exchanger. If you have studied amino acids, then you will know that amino acids have both charges, positive charged group and negative charged group. The carboxyl group is negatively charged and the amino group is positively charged, and that is the reason why the protein is amphoteric in nature. That is, its net charge depends upon pH. Okay, so consider this to be a protein, and when the pH is equal to isoelectric point, then there is no net charge and this thing will not bind to any ion exchanger. Now consider pH smaller than Pi. Okay, in this case, that particular molecule will be having a net positive charge, and that is the reason why it will bind to cation exchanger. Now, considering the principle, considering theory, the solutes which have both negatively charged groups as well as positively charged group should bind both anionic exchanger as well as cationic exchanger. Okay, this should happen. But when one is dealing with large biomolecules, then the pH range of the stability is to be evaluated. Okay, the pH range of the stability must be evaluated when you are dealing with large biomolecule. Now this range of stability of a particular biomolecule is that pH range in which the biomolecule is not denatured. Okay, the range of stability is the pH range in which the biomolecule is not denatured. Now consider a protein. That protein has an isoelectric point of 4. So in this case, you will choose an ion exchanger that can bind to protein in the pH greater than 4. Okay, so in the pH range which is greater than 4, that ion exchanger should bind the protein. And when the pH is greater than 4, the protein is negatively charged, and that is the reason why the ion exchanger must be an ion exchanger, for example DEAE. So in case when the isoelectric point of the protein is 4, you will be using an anion exchanger. An example of anion exchanger is DEAE. Now if you use a cation exchanger in the pH range below 4, then in the pH range which is below 4, many proteins will be not stable and they will be aggregated. Okay, the pH below 4 is very acidic, and in the acidic environment many proteins will not be stable and they will aggregate. So it depends upon the pH. Okay, it depends upon the isoelectric point. Okay, whether you are going to use anionic exchanger or cationic exchanger. In theory you can use both, but in practice you cannot use both. Okay, it depends upon what the isoelectric point of that particular biomolecule is. So in this case you cannot use cation exchanger. Consider a protein who has isoelectric point of 10. Okay, now because of this protein will be positively charged at pH 7. Okay, so you will choose a cation exchanger which is negatively charged at pH 7. Okay, so cation exchanger is negatively charged. So in the pH range of 7, you will use a cation exchanger for this protein who has an isoelectric point of 10. So again, isoelectric point determines whether the anionic exchanger is going to be used or cationic exchanger is to be used. In this case, the cationic exchanger is used. Okay, if we consider to use anionic exchanger, then we have to consider the pH range above 10, and like pH 11, pH 12, pH 13. In that pH, the protein will be negatively charged so that it can bind the anion exchanger. But in that pH range, that pH range is very high and protein will not be again stable, and that is the reason why in this case you cannot use anionic exchanger. So again, whether you are going to use anionic exchanger or cationic exchanger, that all depends upon the isoelectric point of the particular biomolecule. Now this diagram shows how the net charge of a hypothetical protein changes as a function of pH. Okay, as the pH changes, the net charge also changes. So between pH 2 to 6, the net charge is positive, and if the pH goes beyond 6, the net charge becomes negative of that hypothetical protein. Now this point, that is 7, you can consider it is between 6 and 8. This is the isoelectric point. Okay, so below the isoelectric point, that particular protein, that particular biomolecule has a positive charge. Okay, and above this isoelectric point, that particular biomolecule has a negative charge. Okay, so in this range, that particular protein is going to bind to a cationic exchanger as it is positively charged, and in this range, that particular biomolecule is going to bind to anion exchanger as it is negatively charged. Now in this range, okay, between 6 to 10, okay, in this range, the protein is stable. Okay, so that is the reason why this range here is known as pH range of stability. So you will make sure that the pH should be in this range of stability, so that the protein which we are trying to isolate is stable and is not denatured. And as the pH range is between 7 to 9, okay, this is the pH range, right? In this range only the protein will be stable. So in this particular case, you will choose an ionic exchanger. Okay, in this range, the protein is going to be negatively charged. So that is the reason why in this condition, you will be using an ionic exchanger to isolate that particular protein. Now in most cases, what happens is the isoelectric point of a particular protein is not known. Now in this case, the type of ion exchanger should be chosen by trial and error method. Okay, you choose a particular ion exchanger by trial and error method if you don't know the isoelectric point of the protein that you are trying to isolate. Now how do you do that? Well, you take small samples of the solute mixture in a buffer and you equilibrate that for 10 to 15 minutes in separate test tubes, and this separate test tubes contain one of each type of ion exchanger. So you have different test tubes, okay, and in each test tubes you have a small sample in the solution, in the buffer. Okay, you have buffer and in that buffer you have sample. Now in each test tube you will put an ion exchanger, and in each ion exchanger in each tube is different. Okay, so suppose this is containing DEAE ion exchanger, then this will if this is containing the DEAE cellulose, then this will be containing CM cellulose, then this will be containing SP saccharose, and then this will be containing sucrose S. So in each type of test tube you put a different ion exchanger, and in each test tube there is a small samples of the solute in the buffer. Now these tubes are centrifuged or they are let stand, and we do this to sediment the ion exchanger. Okay, So after putting the ion exchanger in the buffer containing the solute, you sediment the ion exchanger by doing centrifugation or by standing it. Now after doing this, you check each supernatant, okay, the supernatant of each tube for the presence of solute, and if in the supernatant there is low level of the added solute, then that ion exchanger is suitable for the use. Okay, the supernatant don't have the solute. What does it mean? It means that solute got adsorbed by the ion exchanger, and with the ion exchanger it got pelleted, and that is the reason why the supernatant don't have the solute, and that is the reason why that particular ion exchanger is suitable for use. If in the supernatant there is solute, then ion exchanger did not bind to the solute, and that is the reason why that particular ion exchanger should not be used. So that is how you do by trial and error method. Now let's talk about the choice of buffer. Now while choosing a buffer, you make a decision about the substances which are going to make up your buffer, then the pH of that buffer, and then the ionic strength of that buffer. Okay, these three decisions you make while choosing a buffer. Now the buffer ions, the ions present in the buffer, interact with the ion exchange resins. Okay, and the buffer ions which have charge opposite with respect to the ion exchanger, those buffer ions will compete with solute for the binding sites on the ion exchanger, and because of that, this reduces greatly the capacity of the column. Okay, the capacity of the column is greatly reduced because the buffer ions compete with solute for the binding site. So cationic buffer is used for anionic exchanger, and the anionic buffer should be used for the cationic exchanger. Okay, if the exchanger is negatively charged, then the positively charged buffer should be used, and if the ionic exchanger is positively charged, then the negatively charged buffer should be used. Okay, it should contain negatively charged molecules, anions in it. That is what I want to say. Now the pH chosen for the buffer first of all depends upon the range of stability of the macromolecule. Okay, what is the range of stability? In which pH range the macromolecule is stable? On that you will choose the pH of the buffer. Okay, that is the primary thing. Now the buffer pH is also chosen so that the desired molecule should bind the ion exchanger. Okay, the macromolecule, the net charge on the macromolecule depend upon the pH, right? So we will choose the buffer pH in such that way that the desired molecule is having a particular charge opposite to the ion exchanger, and that is the reason why that desired macromolecule will bind to the ion exchanger. Okay, now talking about the ionic strength of the buffer, that the ionic strength should be low, and it should be low. Why we keep the ionic strength of the buffer low? Well, to avoid the damping of interaction between the solute and ion exchanger. Okay, there should not be any damping of interaction between the solute and ion exchanger, and that is the reason why we keep the ionic strength of the buffer low. So buffer concentration in the range of 0.05 to 1.0 molar is recommended for that. Okay, so that is all for this video. Thanks for watching and see you next time.